Okay, thank you, Ebru. The critical region has to be satisfied by somebody, either by the operating system or your interprocess communication libraries, or by yourself. Okay, so the last time we were doing this, and we said that why don't we do this? Why don't we? By the way, these are the properties of critical regions. We looked at them. The first one I already told you. No two processes can be simultaneously inside their critical regions. Okay, and you cannot assume that critical regions are so small and my CPUs are so fast. Okay, so I don't think that it is likely to have a switch when I am in the critical region. You cannot assume that. Okay, and if nobody is in the critical region, then the system shouldn't stop me from doing entering the critical region. And no process should have to wait forever to enter its critical region. Number four, it's called starvation, and it can happen. Okay, let's say I have 10 processes, they are sharing the same critical region. Only one of them could be in the critical region, and it turns out that 9 of them using the critical region without no problem, but the 10th one has to wait forever to get the critical region. This should not happen. Okay, so I think we looked at the ways of doing the critical region. One of them is the direct solution, and I'm doing the solution myself. I have two processes, P1 and P2. They are running exactly the same code. Okay, and there is a global variable named lock. If lock is 0, okay, if lock is 0, then I can enter the critical region. That's the rule that I have set as a programmer. Operating system doesn't know anything about this. Compiler doesn't know anything about this. As a programmer, I said that I have written two threads, P1 and P2, and they are sharing this global variable lock. If lock is 0, then I can enter the critical region. So there is a while loop at the beginning. Okay, there is a while loop at the beginning. This while loop says that if lock is not 0, then I will be in an infinite loop. If lock is not 0, then I will be in an infinite loop. So, well, I mean, as a single process, as a single thread, this doesn't make much sense. But I know that I have very similar code running with the thread number 2. If lock is 0 at the beginning, then I can enter the critical region. As soon as I enter the critical region, I change lock from 0 to 1 so that nobody can enter the critical region. And I do whatever I want. For example, that print spooler, I put file A, I increment n, and when I leave the critical region, it is enough for me to just assign a 0 to lock, just reset lock, so that the other processes can enter the critical region. Other processes could be P2 or P1 again. Okay, so what was the problem with this case? Can somebody tell me? What was the problem with this case? Is there a race condition with this picture? Is there a race condition with this picture?
Somebody can enter after the while loop, but before the lock.
Yeah, at this position, okay, if there is an interrupt, after I make sure that lock is 0, I entered the critical region. Just before I executed this instruction here, assigning a 1 to lock, okay, an interrupt might happen. After the interrupt is handled, the scheduler might give the control CPU to P2, and P2 will run into this while loop, and it will see that lock is 0 because I didn't have yet the chance to make it 1. So this one will enter the critical region. So both of them will be in their critical region. That's not good. So there should be one way of doing this thing. I mean, this loop here. Okay, this loop here and this lock, setting it to 1, should not be should be executed in a single run. Okay, while I am executing these statements, there should not be any switch. Somebody has to guarantee that, but as a regular user, I cannot do that because I don't have those kind of, I don't know when the switch is going to happen. I don't know when the interrupts are going to happen. Okay, so this is not a good idea to implement the critical regions. So this is a spin lock. It is called the spin lock. Okay, so lock is updated by somebody else. If lock is not 0, I wait until lock becomes non-zero. Okay, good. So some people say that why don't we do this? It's very smart. I increment lock and at the same time I check it. Okay, so if lock is 0, okay, I compare lock with 0, it is 0, then I can leave this. Okay, I can just, lock is 0, so I can leave this loop right now, right? But before I leave the lock, before I leave this loop, lock becomes 1, right? So that's good if lock is 0. So that means that I both checked if the lock is 0, and as soon as I checked lock 0, I increment it. So I am in the critical region. So I am doing this at the same time. If lock is not 0 when I enter this loop, let's say if lock is 1, so this while loop will keep running because lock is not 1, but I will make it 2 because I incremented it. But inside the loop, lock is decremented by 1, so it becomes 1 again. So I will run this check again. Again, it's going to be 2 and 1, 2 and 1 all the time until somebody makes lock 0. It looks nice. So I am doing these two things at the same time, checking the lock and incrementing it at the same time. So what was the problem? Checking the lock and incrementing it. If the switch happens here, then I am in trouble. Okay, but this is C++. This is not assembly language. Okay, lock not equal to 0 is not done in a with a single assembly language instruction. Okay, so if I compile this into IBM mainframe instructions, this is what happens. Okay, load the value of lock to register R0. Okay, and copy register R0 to R1, increment R1 by 1, store R1 to lock, and compare R0 with 0. So this is lock not equal to 0. As you see, there are 1, 2, 3, 4, 5 instructions going on, and if you include the jump, if it is not 0, 6 instructions for this while loop. Okay, so that means that if an interrupt occurs here or there or there or there, I will be in trouble. There will be a race condition. So this is not a good way of doing it either. I couldn't find a solution. As a regular user, without any help from the hardware, I couldn't find a solution. But that doesn't mean that there are no solutions. People are smart. They worked hard, and during the 1960s, they found many solutions to this problem. And one of them is this. Okay. Mutual exclusion with busy waiting. Busy waiting means that I am running a loop like this. Okay, busy wait. I am busy, I mean P1 is busy, but it is waiting for something. Why is it busy? Because it is running a loop. But at the same time, the purpose of this loop is to wait for somebody to make it 1 or 0, sorry. Okay, so We are going to see this mutual exclusion by busy waiting. Let's say I have two threads, thread number 1 and thread number 2, and they share the same global variable turn. Okay, let's say turn is 0 at the beginning. Let's run this loop. This loop says that if turn is not 0, then see this one. This is an infinite loop. If turn is not 0, I will be in a loop, busy waiting. Okay. I am busy waiting, and this lock will prevent me enter the critical region if turn is not 0. But in this case, turn is 0, so I left this and I am in the critical region now. Okay, I did whatever I want, and I made turn 1, and I am in the non-critical region. Since I am in the non-critical region, I can do whatever I want. This part of the code is okay. Critical region is the region where I need to be careful. No two processes can be in the critical region at the same time. So in order for this process to enter the critical region, turn has to be 0. So it was 0 and I entered it. Let's say before I run this while loop, this one runs, okay? In an infinite loop, this one says that if turn is not 1, I will be in an infinite loop. Since turn is 0 at the beginning, this won't enter the critical region. It will wait because turn is not 1. Okay? It will wait. Let's say this one started again and it entered the critical region. After it is done with the critical region, it may turn 1. Turn is 1 now. Since turn is 1, this one can start running. Critical region, it makes turn 0. As you see, this one enters the critical region, leaves it, makes the turn 1. This one takes the turn, okay? Turn is 1, enters the critical, it makes it turn 0. And this one can enter. So it is called strict alternation. With the strict alternation, there are no race conditions. That's good. Why? Because doesn't matter, okay? Doesn't matter when the switch occurs. Let's say the switch occurred just after the while, before I made turn 1, okay? I'm in the critical region, this one has to wait, okay? If switch happened before the while loop, then this one has to wait. If switch happened during the critical region, this one has to wait. If switch happened just after I made turn 1, then I am out of the critical region anyway, so no problem. Okay, so strict alternation is a good solution to this race condition to enter the critical region, mutual exclusion. Again, this is a busy waiting, and the technique that we use for busy waiting is called spin lock. A lock that uses busy waiting is called spin lock. So this is a spin lock because it spins all the time. Okay, and previously we tried to implement the same thing. There is a spin lock here. Okay, spin locks are nice, but there is a problem with the spin locks. What is the problem with the spin locks in terms of system efficiency? They are inefficient, right? They are wasting the CPU time. They keep checking the same variable over and over and over again until it becomes 1. So you are wasting the CPU time. And it's a CPU bound thing, so it doesn't need anything from the memory other than the turn. So, well, they are nice, they are simple, but they waste the CPU time, and we are going to look at it in a few minutes. So the strict alternation is good, but there is a problem with it. What is the problem? You watch my video. So what is the problem with the strict alternation? What is the problem with this picture? There is no race condition, I know that.
Sir, process 1 is being blocked by any process not in its critical region, so the rule 3 is violates it.
Exactly. Let's say process B is lazy. For some reason, it did not run. Okay, process B is in the non-critical region. Okay, it is waiting there, and it is waiting there. The non-critical region takes lots of time for this process number 2. Okay, that's okay. If turn is 0, I entered my critical region. I made turn 1. I am in the non-critical region. I have completed non-critical region. Top of the loop, I came here. Turn is 1. Okay, it is not 0. Since it is 1, not 0, I need to enter the critical region, but I have to wait. I am waiting for process number 2 to make it 0 again, but process number 2 is in the non-critical region. It is doing something. What does that mean? It means that nobody is in the critical region, but for some reason I cannot enter the critical region. That's a bad thing. That's a bad thing. That violates one of the rules of critical regions. No process running outside this critical region may block other processes. No process running outside this critical region may block other processes. Okay, so that's not a good thing. Okay, we satisfied this one. Okay, no two processes may be simultaneously inside their critical region. We violated number 3. That's because we assume that both processes are running at the same speed. Okay, so we made an assumption about the speeds of the process executions. So definitely rule number 3 is not there. Then there's not a good critical region implementation. But if you know that things are going that way and this is okay, maybe you can use this as a simple solution. But usually we don't prefer this. Okay, so that's the problem with the mutual exclusion. So you did not watch my video? You didn't watch my video? I told you to watch my video. It wasn't there. Okay. So somebody came up with this idea, Peterson solution. Okay. Let's say I have two processes. Okay, there are two processes. Okay, process number 1 and process number 2, or 0 or 1, doesn't matter. Okay, and each one uses this enter region and leave region functions before entering the critical region and after leaving the critical region. So enter region and leave region. If I like to modify this one, okay, I would say take this out and take this out. Okay, I would say enter region 0. 0 is my process number, and enter region 1 and get this out, and this one is leave region 0, leave region 1. So this one says that the process 0 is entering the critical region, process 1 is entering the critical region, process 0 is leaving the critical region, process 1 is leaving the critical region. If somebody else is in the critical region, this will be blocked in here. Okay, the similar here. Okay, that's the idea. So let's look at the enter. So question, if this is the case, tell me where the process A can be blocked. Tell me where the process B is blocked. How many places, how many positions can A and B be blocked? At what line of the code process A is blocked?
Mobile turn isn't 0.
I take it out, I deleted it.
Okay.
I deleted this one, I replaced it with enter region. I deleted this one, I replaced it with leave region. This one is same. So where is the block?
Before enter region.
Enter region is going to be the place where this process A can be blocked, or here enter region. Leave region will never be blocked because I am just leaving the region. Okay, so here what I am expecting here is, why don't I write the same thing here? While true, okay, so enter region, enter region 0, and this is my critical region. Whatever I do it. Then I leave region 0 and non-critical region. And this is the whole loop. So this is process number 0, right? And process number 1 is exactly the same thing. Process number 1 is exactly the same thing. The only difference is P, okay. This is 1 and 1. Why don't I use the red color so that you will see the difference? Okay, so very similar to strict alternation code, but we are not talking about the turns here. Okay, so let's look at this code. This one says that I have two processes, and there is a global variable named turn, and there is a global array of integers of size 2. Okay, turn and interested. Turn, the meaning of turn is the same as before, either the turn number 0 or turn number 1, process 0 or process 1. And interested is actually it's a binary Boolean array. If I am interested in entering into the critical region, I made as a P0, I made the element number 0 to 1. If I am process number 1, I made the element number 1. So I am showing that I am interested in entering the critical region. Okay, so let's look at this one. This is much easier. Leave region. As a process number 0, for example, if I am leaving the region, what I'm doing is that I am just modifying my interested position to false. It is 0. That's it. So I am not interested in the critical region. If somebody else is going to enter the critical region, they should just check this array. Let's look at this enter critical region, enter region. So there is a variable named other. Okay, other means that if I am process number 0, other is 1 minus 0 is 1, right? If I am process number 1, other is 1 minus 1, 0. You understand the logic, right? So other is the process number of the other process. That's good. Okay, so I make my interested process true, just the opposite of this leave region. Okay, just opposite of leave this region. And then I am saying that I am interested in entering the critical region. and the turn of the critical region is going to be the process. If this is 0, then this is 0. But that doesn't mean that I can enter the critical region, because the other process might be interested in entering the critical region. What am I going to do? I check this condition. If turn is the same as process, okay, I am trying to make the turn myself. If this is true and the interested other is true, that means that both of us are trying to enter the critical region. So I will wait. Okay, I am trying to enter the critical region because turn is the same as process, and the other one is interested in the critical region. So I will wait because the other one needs the same critical region too. So the problem here is this: what if the other process is running exactly the same thing? The other process is going to wait until infinity. So both of them will be entering the until the infinity. Both of them are waiting for each other. That's going to be a problem, but that's not going to happen. Why? Why do you think that both of them cannot run this while loop until infinity? One of them has to go out. If both of them are trying to enter the critical region, one of them will succeed. One of them will return from this function and enter the critical region. The other one will wait. Can you tell me why? There are two things that I am looking at.
Turn will be 1 or 0, not both of them. Then
Yes, exactly.
that's why.
Yeah, that's Galip. What you are saying is exactly true. Turn is shared. Either it could be 1 or 0. It cannot be both 1 or 0. Interested other could be both of them are true, right? Because interested is a two-dimensional, is a array of two elements, 0 and 1. Both of them could be true, but turn is a variable. It has to be either 0 or 1, right? So whoever has the turn set to 1 or 0, the other one has to leave this loop, and the other one enters the critical region, and it stays in the critical region. And when it leaves, it makes this interested false. When the interested false happens, then this loop is going to be finished, because now interested other is not true anymore. Okay, I have the turn and I have enter my critical region. So it's like it's kind of a double lock. It's like a double door. Okay, you know those double doors when you enter the. Okay, let's say this is your building. This is your building, and if there is a door that can. Okay, this is the door. The door can open. Why do I? Okay. Let me try to use different colors to explain it. Okay, this is the entrance of the building, and there is a door of color red. The door opens this way. When you open the door, other people come in, not just one. So this doesn't work this way, so I don't like it. Okay, because this is very uncontrolled. It is like maybe like this. There is a box like that. Okay, so the door it opens like that, and the door it opens like that. You take somebody in and you lock this door, and you check if that person is the person of interest, then you open that door. It's kind of like that. So turn and interested are kind of doing the same thing, double doors. Well, it is not exactly the same, but the analogy is kind of, I hope it helps you to understand it.
May I ask, how does this scale? Because this seems that it doesn't scale at all.
Yeah, but you mean if n is 10 or something like that?
Yes.
Well, yeah, well, there is it is not trivial to extend it to more than two processes, but the idea is the same thing, okay? Here, when you say if there are, the idea is again this one. If there are other processes that are interested in getting into the critical region, you check all of them, okay? You check all of them. If there are any of them is trying to enter, then you say that, okay, I'm not going to enter. And since there is only one turn, okay, everybody is sharing it. Depending on its value, one of them will go into the critical region. This doesn't have to stay the same. You don't have to say turn is equal to process. You might say turn is not equal to process. You are changing who is going to enter the critical region, but doesn't matter. One of them only will enter the critical region. Okay, question. Can I do this? Not equal to? Can I do this?
Shouldn't this lead to a starve, a potential starve?
Why not? Why?
Because we set the turn to process and I enter immediately.
We send it to the process, and I am saying that if turn is not the same as the process and the other is not true, but so there is the second condition. Okay? Even if the turn is not my turn, as long as anybody else is not interested in getting to the critical region, I should enter it, right? So I mean, if this is the only condition, then that would be a problem, but it is not. So generalization is not that trivial, but it generalizes, yes.
Okay.
Okay, I think there is a nice exercise at the end of the chapter that asks you to generalize this to more than two processes. But the thing is, the rule number 3 is never violated, because I enter my critical region, I leave it, I can enter it again without waiting for the other process to change stuff. Okay, as long as they are not interested in going into the critical region. Okay, good. This one is good, nice. Again, neither this strict alternation nor the Petersons algorithm, okay, none of them require you to have help from the operating system or from the hardware. Okay, so you handle everything in software. Operating system doesn't know that you are doing your critical region by yourself. And we prevented the race conditions. Okay, we didn't run any test about what if the switch happens here or that. Doesn't matter. I mean, if switch happens before the interested, the other one can go on and enter the critical region. If switch happens after the interested true, then the other one can do the process true and turn process, but it will be blocked at this loop because my interested is true and the turn is the process. Okay, doesn't matter where the switch happens, only one of them can break out of this loop. This line satisfies that. Okay, only one process can break out of this loop, not both of them, and both of them cannot stay at this loop until infinity. Okay, so that means that rule number 1, rule number 3, it's satisfied now. Okay, good. So as I said before, these methods, they don't assume any help from the hardware. What if we get help from the hardware? Our tasks will be much better, much easier. We don't have to write these kind of complicated code. Well, actually, it's not a very complicated code. All you do is just call this function, enter region, and leave region. That's it. But I don't like this spin lock here. Okay, this spin lock makes things inefficient. Okay, since my operating system doesn't know that I am running in a spin lock, I am doing something like busy waiting. Okay, operating system has to give me some CPU, my share of the CPU, but I'm going to waste that share of the CPU in a very tight loop, and I don't like that one. So let's try to get some help from the operating system and from the hardware. Hardware help is this: the TSL instruction, test and set. Okay, test and set lock instructions, TSL. Okay, remember what we try to achieve first when we do this. We are trying to test and set lock. We are trying to see if lock is 0. Okay, if it is 0, just increment it and enter the critical region. That's what we tried to do, but that was a fail because this single line of C++ code translates into more than 6 lines of code. So that was a bad thing. What if hardware gives me such an instruction? That's the instruction, TSL instruction. TSL does this. It loads the value of memory location lock. Lock is just a memory location, just a variable, global variable, into this register Rx. Okay. So it reads the contents of the memory location lock into register Rx and then stores a non-zero value at the memory address lock. So if at the beginning, this is, let's say this is register X value, I don't know, the memory location lock value is 0. So after I run this instruction, value 0 is copied to Rx, loaded, and lock becomes 1. Okay, this is what happens, and this is done without worrying about the switching, any interrupts. Okay, so operation of reading the word into the register and storing the value of 1 into that memory location is indivisible. You cannot interrupt it. This is done like, of course it's not done in a single clock cycle, but you may think it that way. Okay, there is no way that an interrupt can interrupt this operation. Okay, so how did it work again? At the beginning lock was 0, so I transferred lock there, and so at time 0 I have it, at time 1 now I have 0 here, and this one is 1. Good. Okay, so this is one case. How about the other case? What does mean that lock is 0? Lock 0 means that critical region is available. I can enter the critical region. Okay, how about this? How about this? Second case, lock is not 0 but lock is 1. Okay, in that case, of course, 1 will be loaded to register 1, register X. Again, I will write another 1 in here. So two things can happen only. Okay, lock is going to be either 0 or 1. Okay, if lock is 0, this will be the end picture. If lock is 1, this will be the end picture. Okay, let's use this nice mechanism that the hardware gives me. Okay, hardware gives me, and I am going to use this to write some kind of a lock to enter my critical region. Okay, so how does the CPU satisfy this TSL? CPU executing the TSL instruction locks the memory bus to prohibit other CPUs from accessing the memory until it is done. So it is not just disabling the interrupts. It just locks the memory bus so that no other CPU can access this lock. Okay, it's more than that. So do you think that TSL instruction is a privileged instruction or not? What do you think?
It should be, since it's locking the memory bus.
Any other ideas? Well, it looks like loss of power for a user, right? It is disabling the interrupts. It is locking the memory bus. But does it have to be privileged? It doesn't have to be privileged. Why? Because it is doing this for a very small amount of time. It is doing this for a very small amount of time. I mean, there is no way that I lock the memory bus and forget about it. No, I cannot do that because the TSL is run in a very short amount of time, and the memory bus is unlocked again automatically. So there is no way that either intentionally or unintentionally I can do that. Okay? So it doesn't have to be a privileged instruction. Okay? And our yes.
How does it do the locking the memory bus? Like help of the lock variable?
No, TSL is a CPU instruction. CPU is designed that way.
So lock is not a special variable.
No, lock is just a simple global variable. Like this one. Turn is a simple global variable. Interest is a simple global variable. Okay? Or here, turn is a simple global variable. Lock is a simple global variable. That's it. Okay? So this is no different than this instruction. Remember the IBM mainframe instruction? Load lock to R0, right? Lock is a global variable, and I load that global variable to my R0. Instead of doing that, I am doing TSL RX lock. Okay, this is very regular CPU instruction, loading a value from a memory to the register. This one loads a value from the memory to the register, but after doing that, set lock to 1.
So this is the feature of the TSL command, not the variable.
TSL, yeah. TSL is a CPU special instruction.
Special.
Yeah,
Okay.
and that special instruction has to be supported by the hardware, by the CPU.
Okay.
And
So
of course, there should be a way of locking the memory bus. So that's a computer architecture feature.
Okay. Why does it need to save the variable of the lock into the register?
Well, you know, as far as mutual regions are, as far as the mutual regions are concerned, you don't need. Oh, you mean what if you like to see the content of lock first? Is that what you mean?
And why do we need to save the initial state of the lock?
Well, in that case, it is very zero. It is already in the R0 here, right? You just load R0 lock. Okay.
So I mean, why don't we change directly to lock variable instead of saving the initial value into the R0 or RX register?
But remember what
Why
the
do we
meaning
need
of
to
lock. What
save
is the meaning of lock? If lock is
What?
zero, if lock is zero, then I can enter my critical region. If it is not zero, then I have to be blocked.
Okay.
I did not let me show you the
Okay.
let me
I
show
was
you
thinking
what
process
let me show you how we use this,
Okay.
then I will get your question. I think this will clear up your question. So enter critical region becomes 1, 2, 3, 4 lines of assembly code, and leave critical region is just 2 lines. So again, I am doing the same P1, P2, P0, sorry, P0, P1. Let me copy this and let me, how do I duplicate? And did I copy that?
I think you did so.
I did. Let me try to paste it here. Duplicate. What? What happened? Like, come on, tamam. Okay. Take this again. Maybe Control C and Control V. Yeah. Somehow it worked. Okay. Now my code becomes something like this. P0 enter region. Now I don't need to provide this. And P0 leave region. And P1 is exactly the same thing. Enter region and leave region. That's it. Okay. So the enter region function loads lock to register. Okay. And I compare register with 0. Okay. Now if the register is 0, jump not equal, enter region. Okay. If it is not 0, then I will go to the top of the function and I test it again. If it is 0, then I can return because I can enter the critical region now. If lock is 1, this comparison will be false, and I will be in the critical. I will be in the loop, spin lock, in an infinite loop. This loop will continue, okay, until lock becomes 0. To leave the critical region, what do? I just load 0 to lock. So when I enter this critical region, the value of lock has to be definitely non-zero. Right? The value of lock has to be non-zero. Yeah. Okay, so let's look at this. Okay, so this is register. At the beginning of the register value, I don't know. This is lock. If lock is 0, then I will load that value to 0 and lock become 1. I will compare register with 0. I am comparing 0 with 0, so they are equal. Jump not equal will not execute, will not jump, so I return. When I return this from enter region function, I returned it and my lock is now 1 memory location. How about the other way? The other way, if lock is 1, this TSL instruction will load that lock to register 1, and lock is going to be 1 again. I compare this 0 with this register. Okay, they are not equal, so I will jump. And I will do the same thing again until I get a lock value of 0. Okay, which can happen only with somebody leaving the critical region. Okay, so this is some help from the hardware, and it works nicely. I don't have to think about, like Osama asked, does this generalize? Where are the process numbers? Remember, with this one, you need to talk about the process numbers. Okay, my process number is 0 and the others are that and that and that. So scaling this up requires some careful coding. Okay, and maybe using this a little bit more difficult. But this one, I don't have to say that my process number is this or such and such. I don't need to know about the others. All I do is call critical, enter critical region, and then leave critical region. That's it. But again, with this one, I need the help from the operating system. Okay, any questions? Any questions? Okay, if there are so, but the problem of this spin lock is still there. I don't like it. This is wasting lots of CPU time. Very tight loop. Okay, here if somebody else is using the if somebody else is using the CPU, if somebody else is using the critical region, then I am in this loop and I keep running this loop. And the operating system doesn't know that I am in this spin lock, so it is giving me my fair share of CPU, and I end up wasting that CPU time.
Can't we just inform the operating system that, hey, like, I am blocked until this comes?
Yeah, well, we are going to do something like that, yes. I mean, we are going to ask the operating system, sleep me until this lock becomes available. But for that, operating system has to know about the locks, right? But in this case, lock again, a memory variable, a global variable that is shared between two threads or processes. So operating system has to know about this, and we are going to see it in a few minutes. Okay, but before that, let's take some break. Let's be here around 12:39. 12:39. 10 minutes. Okay, so mutual exclusion with busy waiting with the help of the TSL instruction makes writing this kind of code easier. So you get this. The trick is this TSL instruction. It does two things at the same time in an indivisible way. Hardware guarantees that reading the lock variable into the register and setting the lock to non-zero happens as a unit. Okay, and it cannot be divided. No hardware can divide this operation. Okay, Intel, okay, has a different instruction for this TSL. Instead of TSL, it say that I have invented this new instruction exchange. This instruction exchange instruction. So the exchange is very similar to TSL. TSL loads the value to the register and modifies the variable to non-zero. Exchange is very similar. It just says that I am going to exchange the values of register and lock. Okay, it's like swap. Swap in a single clock cycle, you may think it that way. Okay, so load one to register and exchange these and compare. The rest is the same. Compare the value of register with 0. If it is 0, then I can enter the critical region. If it is not, then I cannot. Okay, so exchange is doing a little bit more, but it is not TSL. It's very similar to TSL. So don't get confused if you see exchange instead of TSL. Okay. So spin locks, we have seen it. Two correct solutions. Test and set lock with the help of the hardware. Petersons algorithm. They all both, okay, they both use busy waiting, and that busy waiting is based on the spin lock. Well, maybe this solution is good for short waits. Okay, for maybe a few hundred, a few thousand loops, this is fine. But if I am going to wait for a long amount of time, okay, we need to get the help from the hardware or the operating system, and the operating system has to put us in a blocked state, and operating system should know that I am waiting for that lock to be available. Okay, so for general purpose use, need a solution that permits sleeping. That's what we are going to do. Before doing that, those spin locks has some unexpected problems. What is the problem? It's called priority inversion. We didn't look at the process priorities, but let's say I have two processes, process H and process L. Process H has a higher priority, so the operating system always favors process H. Okay, and process L as a lower priority. If CPU is available, if two of them are ready to run, process H gets the priority. Process H uses the CPU as much as it wants. If process H is blocked, okay, then in that case process L can run. That's the definition of priorities. Okay, so the scenario is like this. Suppose we have two processes, process H and process L. Okay, L never run if H is ready. That's the rule. Okay, while H is sleeping, for example, H is waiting for some data from the desk, PL, process L, it takes the CPU, okay, and it starts running a spin lock. It starts running a spin lock. It is in a loop like this. PL is running something like this, and PL is waiting for something. PL is waiting for something to happen. If PL is waiting for lock to be available, so PL is in a spin lock. Okay, PL is in a spin lock. Then H wakes up. Since H has a higher priority, it wants to get the it wants to get the lock. Okay, so since H has a higher priority, it wants to get the lock, but it cannot. Why? Because process L got the spin lock and it is in the critical region, but it cannot continue to exit the critical region. Okay, it cannot continue because process H gets the CPU. So it spins waiting for L to free it, but L can't get the CPU, so it doesn't progress. Okay, so this is called priority inversion because PL has the resource. It cannot release the resource because it cannot get the CPU. And this happens because of the spin locks. Okay, it happens because of the spin locks. Because operating system doesn't know that H is waiting for something. H is running a loop like this. Okay, so that's called the priority inversion with the spin locks. And when we have time, when we look at the deadlocks, maybe we'll talk about this a little bit more. So just keep this in mind that in operating system world, the decisions that you're going to make might result in very unexpected results, and we have to be careful about our decisions. And once such a thing happens, it would be very difficult to find why it is happening. Okay, so the idea is this: prevent wasting time by busy waiting. Simplest way is sleep and wake up. Okay, so we need to have system calls. Okay, I'm going to call the sleep system call. I make a sleep system call, and I'm going to block myself, and whenever the lock is available, operating system is going to wake me up. Okay, to tell you about this sleeping and waking up approach of solving the critical regions and addressing the race condition problems, there is a classic problem, producer-consumer problem. Okay, the producer-consumer problem is this: there are two processes, okay, two threads. One of the threads are producing some data, the other thread is consuming it. We don't care about the data production. It is a special routine, you might think. One of them is producing it, the other one is consuming it. The important thing here for us is the inter-process communication and the synchronization. Okay, so the producer wants to add elements to the bounded buffer size. Let's say it's like this. This is the producer thread. It produces, and there is a buffer, limited amount of buffer, and the consumer reads it. Okay, this is the buffer. So typical picture for a race condition, they have to share this buffer. Okay, the consumer cannot read this buffer if it is empty. The producer cannot write to this buffer if it is full. So they have to communicate with each other. Okay, if the buffer is full, the producer has to wait or sleep. If the buffer is empty, the consumer has to sleep. Okay, so that's the idea. If we can handle such a picture, such a problem, then we can handle any kind of inter-process communication. That's the idea. So in computer science, specifically in operating system world, there are problems like simplified problems. If you solve that simplified problem, you may solve very complicated problem of the same type. One of those simplified problems is the producer-consumer problem, and we will see other examples of such simplified problems later in the semester. Okay, so let's look at this one. Well, I am trying to hide this. I am trying to hide this title with the race condition. I was going to ask, do you think there is a race condition? But yeah, there is a race condition in this code. Okay, so let's look at this one. Producer, it just produces an item. What is the item type? Let's say it's an integer. I don't care what it is. Okay, and there are 100 buffer positions available. Currently count is 0. There are no elements in the buffer. Okay, so this is what I do. I produce the item. If the count is n, that means that the buffer is full. I am going to sleep. If count is not n, I am inserting the item into the buffer, and I will increment the count by 1 because I just inserted it. And if the original count is 0, that means that my consumer is sleeping on the buffer. Well, if this count is 0, I incremented it, it became 1. So I am waking the consumer. Okay, if consumer must be sleeping on it. And this is the consumer code. Consumer says that if count is 0, then I cannot consume anything. I am going to sleep. Okay, until somebody wakes me up. Who is going to wake you up? The producer wakes you up when count becomes greater than 0. Okay, so if count is 0, then I'm going to sleep. If count is not 0, then I can remove one item from that buffer, and I am decrementing the count by 1. But before I decrement it, if that the original count is n, that means that the buffer was full. Now it is not full, right? Because I decremented by 1. So I am waking the producer. Producer must be sleeping here. Okay, then I am consuming the item. Okay, this is a typical producer consumer stuff. As you see, there are no mutual exclusion stuff here. There is no critical region marked. This one doesn't say that I am in a critical region. Okay, so that's going to be a problem. Tell me the race condition. Tell me how the race condition can happen. I think it is the count, right? Count is the shared variable, and the problem happens with the count, I guess. When there is a switch happens somewhere, I might be in a race condition. Can somebody tell me? I wish I didn't put this arrow here. Okay, so if switch happens there, then we will see the race condition. Can somebody tell me how this race condition happened?
Consumer try to consume something that producer doesn't produce yet.
So how does that happen? If consumer is trying to consume something that the producer did not produce yet, then count would be 0, right? Then I cannot consume it. I would be sleeping, right?
It wakes the producer and then consumes the item.
Yeah, if count is 0, if the buffer is empty, it waits. When the buffer when there is something to consume, then I will wake up and I will remove it. So what is the race condition? Race condition is the result of the whole system depends on who runs when. Okay. So if all the who runs when decisions are right, then this should work fine. But if the interrupt happens at the wrong time, then there is a problem with this approach.
When count is 1 and the two consumer pass the if state and interrupt by simple CPU. Then to consumer try to remove item that, but we have only one item in the list.
When count is 1, is that what you are saying, right? When count is 1, I produce an item. Count is not n.
No,
Okay.
not for this consumer.
You are talking about the consumer. When count is 1, since count is 1, I don't sleep. I remove the item and I say that
Before removing the item, I interrupt.
okay.
Second consumer.
Well, there are no two consumers here. There is only one producer and one consumer. There is only one producer, one consumer. The point is here. If count is 0, I am going to sleep, right? If count is 0, before I sleep, let's say interrupt occurred. And the scheduler said that producer is going to run. Producer runs, it produces an item. Count is 0, I don't sleep. I insert the item, okay. And I said that count is 0, I will increment it. Now count becomes 1. But since count was 0, I wake the consumer. Consumer is not sleeping, right? Because it did not execute the sleep function yet. Switch happened here. Okay? So it will try to wake the consumer, but the consumer is not sleeping. So this wake up call will be ignored, or there will be a system crash, I don't know. It will be ignored. So it said that wake up the consumer, then switch happened. When the switch happened, consumer says that, okay, I am going to sleep. Consumer sleeps, and next time the loop happens, count is not 0 anymore, and I don't wake the consumer. Right? So consumer continues sleeping, and when count reaches n, the producer sleeps, and both of them are now sleeping. So that's a race condition, and that's a deadlock too. Both of them are waiting each other. Okay, so there is a race condition with this code, and we are going to solve it. So what would be the solution? The solution would be make this count 0 sleep, okay, or count and sleep. It is the same thing. Okay, count and sleep, both of them, sleep and sleep, in a critical region. Okay, so begin critical region and critical region. Okay, since those things are happening here, again the begin critical region and end critical region, I should have done that, but we are going to do that in a new way using the semaphores. Okay, semaphores invented 1965. There are two operations, up and down, okay, and we get help from the hardware and the operating system. So we ask the operating system or the thread library saying that I need a semaphore. Semaphore is simply a counter, actually, a counter, just like an integer s. This is a semaphore for me. So what can I do with an integer? I would increment it or decrement it. That's it. Okay, special integers, I just increment it or decrement it. So the operating system gives me these two operations, two operators: decrement the semaphore or increment the semaphore. So what is the function of down? Down says that, okay, I will decrement the semaphore variable if it is greater than 0. If it is 0, I cannot decrement it. It's a positive integer. I cannot decrement it. So I will go to sleep. I will sleep, okay, until somebody increments this semaphore to make it 1, so I can decrement it and make it 0 again. Okay, so down just decrements the variable, the semaphore, by 1. If it is 0, it sleeps. It waits for somebody to make it 1. In that case, when it becomes 1, it can wake up and decrement it to make it 0 again. Okay, so down potentially can sleep when you make the semaphore down. Up is doing just the opposite. It increments the semaphore. It just increments the semaphore. And if a process is sleeping on it, if a process is waiting for this semaphore to be to become 1, okay, then it will wake it up. Okay, so it's a wake up. So down potentially can sleep, up will never sleep. When you call up, it will increment the semaphore. If somebody is waiting for it, if somebody waiting for that semaphore to be incremented, then it wakes that process up. Okay, and it generalizes very well to multiple users of the semaphore. So many processes can decrement and increment these semaphores. Again, I can use this as a critical region guard lock, or I can use this to communicate information between the processes, especially for the producer consumer problem. Okay, let's see our code, producer consumer code, using the semaphores. Again, semaphores are from the operating system or our interprocess library. When I say up and down, they are down in an indivisible way. Okay, decrementing it, going to the sleep, is done in a indivisible way. Remember what I said? Okay, if count is 0, go to sleep, and if count is and go to sleep. We said that if these were done in an indivisible way, we didn't have any problems. Semaphore is kind of satisfying that. Okay, and standard thread libraries provide semaphores for you, and you get the semaphore and you use them. You create a semaphore, and there are only 2 operations on a semaphore: down the semaphore and up the semaphore. Decrement integer, increment integer. Decrementation can cause sleeping sometimes. Incrementation never causes sleeping. Incrementation can wake up some of the processes. Okay. So semaphore, mutual exclusion 1. Semaphore is the type of the semaphore. Okay, that MEX is my variable name, is the semaphore name. At the beginning, its value is 1. Okay, so I down mutual exclusion semaphore by 1. It becomes 0. It doesn't get blocked because it is 0 now. It decremented. I am in the critical region. Okay, after I leave my critical region, I up the MEX. Okay, when I am in the critical region, since this MEX becomes 0, nobody can enter the critical region using this MEX, because since the value is 0, when you try to decrement it, when you try to down it, since it is 0, it will sleep. It will sleep until somebody ups it, increments it. That means it is myself. After I am done with the critical region, I increment the semaphore. Okay. Well, in this case, it looks like I am just using 0 and 1 for the semaphore values. If you are using only 0 and 1, this is called mutual exclusion or mutex. Mutex is just a special semaphore that can take 0 or 1 value. So it's a binary semaphore. Binary semaphore is mutex. And thread libraries know about these. You ask the thread library to give you a mutex, they will give you a mutex. You ask the thread library to give you a semaphore, they will give you a semaphore. Semaphore are for counting, mutexes are for 0 or 1. Okay. So the implementing semaphore is typically done in the kernel. When the semaphore runs, okay, up or down semaphore, your operating system, with the help of the hardware, masks the interrupts while manipulating the semaphore. On multiprocessors, okay, they use test and set lock protection so that the system bus is locked. Okay, since both of them are only few microseconds, it's not a serious problem. Okay, so semaphores, mutexes are implemented in the kernel with the help of the operating system hardware. Okay, so this is a producer-consumer problem. Producer-consumer problem with semaphores and mutexes. Okay, so I have 1, 2, 3 semaphores. Okay, I have 3 semaphores. Their values initially are 1 and 0. So producer is going to produce some numbers, items, and I will put them in a buffer of size 100, and consumer will consume them one by one. So there are 100 buffer positions available. Empty is a semaphore. Okay, it will count the number of empty slots. Full is another semaphore. It will count the number of full slots. So always empty plus full will be equal to 100. Mutex is going to be our mutually exclusive semaphore. We are going to use it to enter the critical region. Okay, so this is the code. I produce an item in the producer. This is non-critical region. And I down empty. I say that decrement empty by 1. If it is non-zero, then okay. At the beginning it is n. So I decremented it, so it became 99. Okay. I down the empty. If it is non-zero, I will be okay. I will come here. If it is 0, then I will be blocked. Remember the semaphores, they are blocked if the semaphore to be decremented is 0. I will wait until somebody ups this empty, which will happen here in the consumer. See? It happens here. If I can achieve this, if I can decrement empty by 1, okay, if I decrement empty by 1, I will down the mutex, mutual exclusion stuff. So if mutex is 1, I can decrement it, and I can enter my critical region. So this is my critical region, and this is my inner critical region. I entered the critical region. I inserted the item into the buffer. And I up the mutex, so I am not in the critical region. Buffer could be used. And I up full, I increment full by 1. Why? Because I have inserted an element into the buffer. Okay. Up mutex and up full means that I am incrementing this value and this value. Mutex could be 0 or 1. I decremented this mutex, I incremented it. Okay. So good. So I did that. Consumer is just doing the opposite. Down full. Down full means that at the beginning full is 0, right? At the beginning full is 0. Well, what does that mean? If full is 0, I cannot decrement it. I have to wait. Why am I waiting? I am waiting because the buffer is empty. Okay. So I will wait until the producer produces one item and it increments full by 1 here. Okay. It increments full by 1 here. When it increments it, I can down this one. I will wake up and I will try to get the mutex. Okay, I will try to get the lock If the lock is available, if the producer is not in the same critical region, I will down it, I will remove the item, and I release the mutex, and I increment the empty by 1 because I removed one item from the buffer, and I consume it. So this is my non-critical region. This is my non-critical region, and this one is non-critical region in both of the loops. Okay, good. So this is an example, producer-consumer example with no race conditions implemented using the help of semaphores. One semaphore is a special semaphore. We call it mutually exclusive semaphore, mutex. Okay. The other two are regular integer semaphores. Some of you might ask, why did we need to use 3 semaphores? Is one of them not good enough? Well, I need these two. Okay. I need these two to make a decision if the buffer is available to write, if the buffer is available to read. Okay, what is the condition that the consumer can be blocked? It is blocked if the buffer is full. Okay, if the buffer is full. Well, I mean, mutexes work in this way. Mutexes can block you only if the integer mutex is 0. Okay, that's why I need a mutex that reaches 0 when the buffer is full. So similarly, to be able to block the producer, I need a semaphore that reaches 0 when the buffer is empty. That's why I have this. So I need this empty semaphore to block producer. I need this full semaphore to block the consumer. Why do I need this mutex? Okay, I need this mutex because both of these producer and consumers, they cannot be at this position at the same time. They have to wait for each other, because while you are inserting an item, you are changing your buffer. Okay, so how do you write some element to the buffer? There should be an in position and there should be an out position, right? You need to modify them, in position and out position, writing stuff and reading stuff, and I have to do this in a critical region. That's why I need this mutex, that one and that one. Okay, question for you. Maybe you have a question. Do you have any questions? Do you have any questions? So nobody has any questions? Okay, I'm going to ask you a question then. If my buffer size is just 1, instead of having 100 buffers here, if my buffer size is just 1, can I get away with using only a single mutex? So my buffer size is just 1, and
Yes.
I am saying that I don't need this empty and full. Get rid of this one. I am going to delete all of them. Okay, get rid of this one, get rid of this one, that one, and that one. Is this okay?
I think you need 2, not only 1.
I need a second. I need a mutex, or I need a second mutex, or I need a second semaphore.
You need you may need like 2 semaphores, but not the mutex.
I need 2 more semaphores.
So empty and full, but not mutex.
One semaphore, but not so two semaphores, and that's it. Is that what
Yes.
you are saying? Oh, you are saying that don't do that. Okay, you are saying that don't do that. Just get rid of this mutex. Is that what you are saying?
Exactly. That's what I'm saying. Yes.
Okay, and get rid of this one. So you are saying get rid of these lines. No, this one and this one. So and n is just one. Does this work? Any ideas, people? So it looks like I am using this empty and full as a mutual exclusive stuff. Okay, so Usama, what you are saying is you need two mutexes, not two semaphores. Okay, because you started them with one. They could be either one or zero.
Sure.
Right? So it is if the buffer is empty, then I will go in there and do whatever I want, and I say that it is full now. If the buffer is full, then I go there and take it out. So the buffer could be either empty or full. It cannot be both full and empty, right? So in this case, it is behaving like a mutex, two of them. Okay, good. So this is a good
But
good
first,
exercise. Yes.
if you have only one mutex, it's also okay. I didn't understand.
That's the
Because
question
there
that
is
I am
only
asking you. Is
there is
it
only one.
okay if I have only a mutex?
I think yes, because there is only one spot, so one is gonna block and the other will wait, and it's gonna be the vice versa.
How about the buffer size? I mean,
I think it's not.
if I have a single mutex, if I have a single mutex, if my buffer size is 1, the producer can keep writing to the same buffer over and over again, because it doesn't try to see if the consumer has consumed it.
Exactly. And the consumer can still consume the whole other things as well
Yeah.
without checking for it.
hmm So one mutex is not enough. I need at least two mutexes if my buffer size is 1. Okay. The important thing is that maybe you could have said, why are we keeping two semaphores here? I keep two semaphores because the only way for a semaphore to be blocked is when it reaches 0. Okay. You cannot say that block me if this number is 100. Okay. If there is a way of doing that, okay, if there is a way of doing like block me if this number is 100, then only one counter would be enough as a semaphore. But the semaphores doesn't work that way. They work only, semaphores doesn't work that way. They work only if the number reaches 0. Okay. So we have two different types of semaphore in this case. We have um, counting semaphores like this one, empty and full, counting semaphores. Okay. And we have mutual exclusion semaphores like this mutex, this one. And your thread library knows about the distinction. Okay, there is a name for it. There is semaphore means that it's a counting semaphore. Mutex means that binary semaphore. Okay, so mutexes are a special case of semaphores, useful when no counter is needed, so only a bit is enough. So implementing the mutex is very easy with the test and set lock instructions. Okay, you try to grab the lock. If successful, if unsuccessful, then you let another thread to run using the thread yield function. If you fail to acquire a lock, you just call that function. And this is an implementation of the mutex, not semaphore but mutex. So this is how it works. Let's look at this mutex unlock. Okay, so you move 0 to mutex. So mutex is a memory location that can take two values, 0 or 1. If you like to unlock a mutex, you just move 0 to there. But if you try to get the mutex lock, so TSL load the mutex memory location mutex to register and store 1 into mutex. Compare 0 with register. If they are equal, okay, if they are equal, that means that I got the lock. So I just jump to OK and I return. Otherwise, I call thread yield. What do I mean by otherwise? Otherwise means that I couldn't get the lock because register is not 0. It is non-zero, it is 1. So I call thread yield. What does the thread yield do? It tells the thread scheduler that I need to be sleeping. I am going to sleep until somebody wakes me up. Okay, so who's going to wake me up in this case? I mean, up here mutex unlock doesn't wake me up. Okay, it just makes mutex 0. So one way or the other, the scheduler is going to let me run again because I am ready to run. Okay, the scheduler let me run again. I jump to mutex lock and I do this test again. If I am successful, I will return and I will continue. If I am not successful, again, I am going to yield the CPU again. When I yield the CPU, somebody else is working on this mutex lock, and eventually, I hope they will release it. But I know that they will release it because I have written the other thread myself too. Remember, threads are cooperative. They are cooperating with each other. So, okay, so these are the assembly instructions for implementing the mutexes. Any questions about this implementation? You understand why I did not make a wake-up call at this position, right? I know that this one has yielded the question. When you yield the CPU as a thread, what would be your thread status? Would it be running, ready, or blocked?
Running.
When you yield the CPU.
Blocked?
Somebody said running, no. Somebody says blocked, no. It is ready. It is ready because you are yielding the CPU. You say that, okay, question. I am removing this line. Does this mutex work?
Yes, but the CPU will be always busy with this thread.
Yeah, it will work, but CPU will be unnecessarily busy with this thread because it's a spin lock. We didn't like the spin lock, right? It will keep checking the mutex if it is available. If it is not, then it will go to the top of the loop and do that. So that means that I am always ready to run. By doing this, I put myself in the ready queue. Okay, whenever the other threads are done, the scheduler will put me in, will choose me, and I will use the CPU again. So this is in effect, okay, this is in effect a spin lock, but this is a much more efficient spin lock. It says that if nobody else has anything to do, I can spin this lock, no problem, but I am going to yield the CPU because I am waiting for somebody else to make this mutex 0. Who is that going to be? Somebody who's going to run this mutex unlock on my mutex. Okay, good. Any questions? Are there any questions? Well, if there are no questions, then I will stop here. I am out of time. We will continue on Monday. But I am kind of disappointed because, I mean, I ask you to watch my videos and nobody's answering me about my videos. What's going on? You are not doing my instructions. I asked you to watch the videos. You did not watch it?
Actually, not sir, because we spend our time to make our homeworks. Actually.
Well, I didn't ask you to stop doing your homeworks. I mean, yesterday morning it was your class time and you could have used your class time to watch the video. I mean, I kind of went over these topics, but I could have started, I could have started from condition variables today because maybe I should have done that. Anyway, okay, don't do that again. I'll see you next week.
Thank you, sir.
Bye. Bye.